Today we'll be discussing exam question 16 for Dr. Petrov's Psych 5612. The question that we'll be presenting on today is, what are dynamical systems? Explain briefly the notion of attractor in state space, and present briefly the dynamical systems hypothesis. I'm Philip Lenos, the presenter, and the two discussants are Caitlin Snyder and Alex Price. So first we're going to answer, what are dynamical systems? Dynamical systems are a mathematical conceptual tool to model cognitive skills and abilities that differ from information processing models in respect to certain fundamental aspects. We can understand how organisms respond to the environment and orient themselves in it without assuming that there are internal cognitive systems that carry out specific information processing tasks. With that being said, the first point to defining a dynamical system is that a dynamical system is any system that evolves over time in a law-governed way. This alone isn't really a great definition because a Turing machine, by this definition, would be a dynamical system. So the second part of this definition of defining a dynamical system would be a system that can be studied conveniently using the tools of dynamical modeling. And dynamical modeling exploits powerful mathematical machinery to understand how certain types of natural phenomena evolve over time. For example, Newtonian mechanics or HVAC system, which we'll further explore when discussing attractors on the next slide. So next, Bayesians of attraction. To understand Bayesians of attraction, you have to understand that there's an evolution through time in state space via trajectories. So this figure shows a state space, and there are trajectories heading towards the center of that little valley-looking object, which would be the Bayesian of attraction. And that little ball with the arrows are showing the velocity vectors and therefore the trajectories towards the center of that Bayesian of attraction. On the next slide, we'll see a better example from top down. And a Bayesian of attraction is a region of space where many trajectories converge, like this figure. And an example would be the Newtonian mechanics we discussed when defining dynamical systems, and also setting the temperature for your home HVAC system, in which the set temperature would act as the attractor. So this center point, the Bayesian of attraction, would be your set temperature, and any deviation away from that would cause trajectories to kind of push that back towards the center. And finally, nonlinear dynamical systems are systems with multiple Bayesians of attraction that split up the state space and its respective trajectories. And this would basically just create a state space with a different spread of trajectories, kind of pointing to either or of the Bayesians of attraction. Next, we're going to talk about the dynamical systems hypothesis. To understand the relevance of the dynamical systems hypothesis, we will discuss an early proponent of dynamical systems hypothesis by Gelder. Gelder suggests that cognitive scientists are trying to reverse engineer the mind to work out how the mind is configured to solve problems that it deals with. They reverse engineer by assuming the mind is an information processing machine. He suggests that this isn't the best or the only way. So Gelder suggests the dynamical systems hypothesis by observing the Watt machine. The Watt governor. The governor feeds back by speeding up as the machine does and respectively shutting a steam valve to control the machine. We'll see a figure on that on the next slide. Gelder's approach to solving this problem is to employ task analysis by breaking the task of regulating the speed into subtasks. They then assume that these subtasks are carried out in separate stages and work out an algorithm for solving the problem by successfully performing the subtasks. Now, this is a nonlinear dynamical system in the figure, as stated in the previous slide, and it's basically just showing that there can be two Bayesians of attraction that affect the trajectories. And finally, the features of the hypothesis are the representational, the computational, the sequential, and the decomposable. So the representational feature states that it can't work without some way of representing the speed of the flywheel, pressure of the steam, and the state of the valve. The computational feature states that the algorithm is a process for comparing, transforming, and manipulating representations of the representational aspects. And the sequential states that it works in a stepwise manner. So, for example, it starts with the resistance, and the flywheel affects the speed, so the spindle, and causes spindle turning, and the spindle arms then cause the linkage mechanism to affect the valve, open or shut it, and then it affects the steam pressure, which then feeds back into the flywheel, and it can directly affect the spindle arms and the amount of speed that the flywheel is causing. And finally, the decomposable feature, which states that it's made up of distinct subsystems and each is responsible for a particular subtask. And that is my presentation on dynamical systems. Thank you.